our CS seminar. It is a particular great pleasure for me today to welcome Judea Pearl as a distinguished speaker to our seminar. Judea needs no introduction, but I will say a few words. So Judea is a UCLA professor in computer science and statistics. He works in artificial intelligence, in human cognition and philosophy of science. He is credited in the invention of Bayesian networks, which revolutionized not only artificial intelligence, but became a very important tool in many other branches of engineering and the natural sciences. He subsequently realized that when he realized that Bayesian networks do not capture causality, he went on and created a mathematical framework for causality. And this has a significant impact on statistical, health, and social sciences, and is now even a vibrant new area in machine learning. Judea is an author of 3 fundamental books: Heuristics in 1983, Probabilistic Reasoning in 1988, and Causality in 2000, and the new version, the new edition in 2009. More recently, he co-authored Causal Inference in Statistics in 2016, and the Book of Why, which brings causality analysis to general audience. He is the recipient of numerous honors and awards, and I will mention only very few. He is a member of the National Academy of Science and the National Academy of Engineering, a fellow of Cognitive Science Society, the Royal Statistical Society, and AAAI. In 2012, he won the Alan Turing Award for fundamental contribution to artificial intelligence through the development of a calculus for probabilistic and causal reasoning. And even just recently, 2 weeks ago, he won the Spanish BBVA Frontier of Knowledge Award for laying the foundations of modern artificial intelligence so computer systems can process uncertainty and relate causes to effect. Finally, and on a personal note, Judea has graduated 28 PhD students, and I was one of the earlier students, the 6th. So now the subject of his talk for this morning is the science of cause and effect from deep learning to deep understanding. Welcome, Yuda.
Thank you, Rina, and thank you all for being here. I'm glad to speak at Irvine. I think it was 3 or 4 or 5 years ago when I last spoke there. And I must first apologize for not having a clear idea of the background and preparation of the audience. So I will speak to you as experts on machine learning, as if you were a typical machine learning person, like the one I meet on my Twitter account. I know that I'll be leaving out many of you who are either more advanced in causal reasoning than the average, and others that are totally against causal reasoning. But I'll just speak to a typical machine learning person as I talk to you. Okay. Now, what I'm going to introduce is something which is quite strange to machine learning, and this is a scientific thinking, which is not very well adhered to in the normal machine learning circles. And I try to be provocative for having a secondary title here, from deep learning, which every machine learning person is deeply proud of, to deep understanding. And I will define what I mean by deep understanding. And this is something that I see lacking in the typical machine learning work. It's a deep understanding. So with this introduction, I'll go to my outline and tell you what the agenda will be for the next hour. I will define what scientific paradigm is, and within this paradigm, I will present to you what I consider to be the two fundamental laws of causal inference. CI will stand for causal inference. Among a derivative of these two fundamental laws will be a ladder of causation, which is a hierarchy of reasoning, which some people think is the DNA of causal inference. And within that scheme, there will be an engine, a do calculus. This will be an algebra of interventions. This will be the engines that will produce results based on the input and the query you presented to it. Then I will talk to some application, and I will convey to you, number one, what the science add to machine learning. The primary addition would be ability to combine data from prior causal knowledge and many data sources. I label it 7 pillars of causal wisdom. These are the tools, partly applications that we can do today, which we couldn't do 2 decades ago. And the future horizon of where I think not machine, but the causal inference is going. And I will focus on 2 endeavors. First is personalized decision-making, and the second will be social intelligence. The reason I put them down is because I'm recently excited about them, so I'll be more vivid when I speak about them. So I'll be more excited to talk about them. But there will be other applications as I go along. Okay, I'm about to talk about the scientific paradigm. And when I talk about scientific paradigm, I would like to mention that within the data science community, there is a tension. There is a tension between what I call the scientific paradigm, which I'm going to define here, and the other paradigm, which is data-driven paradigm. Now, the scientific paradigm is characterized by 2 components. First, you have a world, and then you have a research question about the world. And the exercise is to think about what should the world be like before I can answer my research question about the world. Now I'm going to contrast it with what I see normally being exercised, and this is the data-centric paradigm, which goes like that. How best to fit the data so as to maximize success on a training set. I'm using here terminologies that are common in machine learning: training set, fitting data, okay? How best to fit data, and there is always some goal of maximizing success, maximizing fit, avoiding overfit, how best to succeed on a training set. Sometimes you split the training set. So it's again within the training set, you just split. Good. But notice here that we are talking about something totally different. Here we are talking about reality which exists outside the data. It's a world which I'm going to model soon, which is an entity like God, sitting outside the data, generating the data, never observed, but existing there hypothetically, generate the data, and I have research questions, not about the data, but about that hypothetical world. It might sound strange, but this is what drives our understanding of understanding. So let's look at what we expect. Once we get a deep understanding, what do we expect that state of knowledge to provide us? First, it gives us a sense of being in control. When you understand how a television works, you feel you're in control, because if it stops working according to the manual, you know how to fix this, what side of it, what technician to call. Okay. It's all part of being in control. You know how to repair it if it doesn't work according to the expectation. You can also predict the future once you have a state of understanding. You can predict the consequences of contemplating action, and you can provide explanation of unanticipated event. I already touched on this, right? And you can imagine alternative world of a road not taken. For instance, if I understand how aspirin works, I can say, what if I didn't take the aspirin? Would my headache be gone as well? And most important, actually not most important, but it's one of the major achievements of science, is you can design new experiments and seek new observation, actually purchase new observations according to what the theory provides you. It enables you to control attention. Attention means to distinguish a informative source of information from a non-informative. Manage your curiosity and generate conjectures. If I just go to the history of science, remind you that most innovative experiments generated with theory that was wrong. Okay, that's important to keep in mind. Like my best example is the Aristotle's measurements of the radius of the Earth that took place about 200 BC in Alexandria, and it was triggered by the idea, by the Greek perception of science at that time, which was totally wrong. They imagined that the sky is an opaque shell through which we see not stars as the objects, but we see holes poked through which we see the eternal light. That we imagine that we are walking on a turtle shell. And he figured out if we are walking on a turtle shell, then a turtle shell must have a radius. If there is a radius, then the light from Alexandria will come to Earth at a different angle than the light at Aswan Dam. It's now Aswan Dam. At that time, it was called a different name. And he can measure the difference between the two angles and figure out, giving the distance, figure out the radius of the Earth. Such innovative, creative experiments was generated by hypothetical theories that have nothing to do with real life, but they generate this feeling of being in a state of understanding. And this is also what drives children in the crib when they engage in playful manipulation of toys. Okay? It drives them to achieve a state of understanding with given the feeling I'm in control. I know which toy rattles and which one stays quiet. Okay? And I know why. And children, as opposed to most animals, okay, have this curiosity, which means they keep on playing and learning about the environment, even though there is no payoff of return. Even when the environment is payoff neutral, they keep on playing and manipulating until they reach this state of understanding that I'm going to formulate soon. Okay. Now I'm talking about causal questions because we are dealing some of the levels that I managed before had a flavor of causation. So what do we mean by causal questions? Here are typical causal questions. How effective is a given treatment in preventing a disease? Was it our new tax break that caused our sales to go up if you are in a marketing business, or was it our marketing campaign? What is the annual healthcare cost attributed to obesity? It was a big issue a few years ago in the New York Times. Can hiring record prove an employer guilty of discrimination? Highly popular topic today when we talk about computer fairness. Yes. And the last one has to do with personal decision question. The personal decision. I'm about to quit my job. Will I regret it? So it's the uniqueness about this question is, it is me. I already made decision from this fact that I am about to quit my job. You know something about my work environment and my degree of satisfaction. Will I regret it? Okay. Now, I colored with yellow here a certain relationship which have a stain of causality. I recognize them from 5 miles away because I attuned myself to recognize them. I trained myself to recognize them. What's special about them is that they belong to a new dimension of knowledge, one that science has not provided us with a language of articulating. I'm not talking about answering those questions. I'm just questioning our ability to articulate them formally in some formal language, mathematical language. Why has science been so unfair to us? Because the science since the time of Galileo and Vieta was married to algebraic equality. And algebraic equality is symmetric operator, which means that if you have atmospheric pressure X and Y is a deflection of the barometer, okay, then Y equal to A of X is equivalent, according to algebraic symmetry, to X is equal to Y over A. There's no preference to one direction over other. And still, you and I understand that it was the atmospheric pressure that made the barometer move and not the other way around. One way to prove it to you is try to manipulate the barometer and see if you can make the rain come tomorrow. But I'm not talking here about proving or disproving theory. I'm talking about just speaking, expressing in mathematics our general consensus that it is the atmospheric pressure which causes the barometer to move and not the other way around. We don't have in mathematics a connective to express this asymmetry. Now we have, in computer science, we call it assignment operator. But it came into science quite late. Only in the 1920s was the first time that you find a distinction between the equality sign and the assignment operator. So what do I mean by assignment operator? I mean that nature looks at the atmospheric pressure multiplied by some constant and determined the amount of movement on the barometer. In that sense, I mean by assignment. Nature assigns values to variables. Okay? Who was the first one to do that? It was Sewell Wright. He was a geneticist. He was interested in the behavior of guinea pigs in the laboratory. He was so fond of guinea pigs that his students tell that one time he wiped the blackboard with his guinea pig, but he also was fond of mathematics. And what he did was something like that. He decided that he wants to find the causal relationship between the genes, or perhaps a manifestation of the parents' color of the fur of the guinea pig and the offspring. Okay, so he put the coefficients here on the arrows. First, he put arrows and said, "I want the causal relationship between these variables," and he succeeded in finding those coefficients from the correlation that he had seen between generations, across generation. And of course, he got attacked right away by statisticians and say, "What are you telling us? That you can get causal relationship from correlation?" And he kept on defending his position, and he said, "No, I'm getting the coefficients, which are causal entities, from a combination of assumptions that I make here in the graph and the data that I see." Okay, but he couldn't articulate his assumptions clearly. And the next slide tells us what modern causal models add to what Sewell Wright did. He was the inventor of the assignment operator in mathematics by using the error. But what we can do today is more general. We can have today a general causal structure, which I call SCM, structural causal model, which is more general in several dimensions. First, it's not tied to linear models, which Sewell Wright was. And it has two beautiful properties. First, it's an oracle of all causal statements. What do I mean by oracle? I mean, it assigned a truth value to every statement in this language. If you want to ask, for instance, was it the aspirin that made my headache go away? This oracle, if you have it, will assign to it a yes or no answer. It's the same oracle that we have in logic. What is the oracle in logic? It's a truth table that you assign values to every combination, every instantiation of the variables. What is the probability oracle? It's the table, huge table. The rows constitute assignment of values to all the variables. And on the right-hand side, you have a number that happen to sum to 1. So you decorate those with numbers. Once you have this truth table, you can assign either a probability or truth value to every query that you can conceive in that language. So this particular element, SCM, serve as an oracle for all causal statements, including counterfactual statement. It's a beautiful property. Why? What makes it so beautiful? It is so parsimonious. It doesn't require a table of all possible queries and all possible answers. It's condensed in something so simple that everyone can construct one in the office or on the computer. And it is rooted in human intuition. That's another beautiful properties. Because what is it? To construct it, you have to ask yourself very, very rudimentary and simple question. Here are the questions. Here is a variable. Who does he listens to? The only primitive is listening to. We have a society of listeners. Those are the variables in the universe. Each one listens to all the others, and the function that relates to them is unique to that variable. So every variable has a function that relates its value to what he or she listens to in the environment. Something very simple. Like if I ask you for instance, who does your headache listens to? The answer would be to the amount of aspirin in my body, to the kind of television program I watched right now, to the kind of good or bad news my wife brought me. Those are the variables that determines whether I have a headache or not. Okay, it is not a function of the stock market in Hong Kong, because I'm not listening to that. Okay, so this primitive, who listens to whom, is the only requirement, the only judgment you need to resort to when you construct that oracle. Imagine constructing such a powerful oracle on the basis of one elementary, rudimentary, and intuitively meaningful relationship, such as it listens to. So now we imagine the universe being a collection of listeners, and now this is just interpret. We can define now what the assignment operator is on that entity. The U's here are unique to every variable. Those are the variables which do not need explanation in my level of description. I decide to leave them undetermined. Everyone listens to others, but UI doesn't have to have a function. That's a difference. It's exogenous. In the graph, which you can plot very nicely, those are the root nodes. Okay? So what is a causal graph? It's an abstraction of a model. If you have a collection of such functions, you just write down who is a variable of who is the argument of what function, and you get yourself a graph. I'm going to demonstrate to you the graph in a second and see what you can do with it. Okay. So this is a beautiful oracle, okay, and most powerful. And I'm going to claim that once you have this oracle, you have a computational model of understanding, by virtue of the fact that you can answer all these questions. So this will be my formal definition of understanding, being able to answer queries on the three level of the hierarchy. That is my definition of having an understanding. Okay, now I promise you the two basic laws of counterfactual. If you take the model, I'll show you how you can compute easily counterfactual. Well, let me first just give you the two laws, and I'll go and describe them. Yes, that's the first law. The second one is the law of conditional independence. Every time you see a separation in the graph, it implies conditional independence in the probability, namely in your data. Okay. So these are the two basic laws. And now I'm going to explicate what they mean. The first one means that this is the counterfactual term. It's the notation is subscript. This means the value of y had variable x attain the value small x for situation u is equal to something which can be derived from the model. How? Take the model, mutilate it, and create a mutilated model in which the two arrows going into X are chopped away, instantiate this variable to X, this is the antecedent, and compute the value of Y. What you compute for Y is what we mean the counterfactual. What Y would be like had X been small x. Here it is on the graph. You start here. This is your society of listening agents. Each one listens to a family of others. You want to know what the counterfactual is? What Y had X been a different value? Chop the parents, look at Y, and compute Y in the mutilated model. This is the definition. This is the first law of counterfactual. I'm just saying it now in words. The sentence, Y would be small y in situation U. Had X been small x, we denote it like that. It means small y is the solution for Y in the mutilated model M sub X with input U. Okay, now you have a definition of counterfactual. You are mighty powerful because you can now assign truth value to every conceivable causal question you can think of. I'm sure you enjoy the power that I've just described to you. Every time I look at it, I say it's a miracle. Anyhow, now if you look at the kind of truth values you assign, you find that they lie on the three loosely interacting levels. Okay. The easiest one to understand is association. That's when you don't even touch the model, you don't mutilate it. You just want to ask the question, what if I see? What if I see a symptom? What can you tell me about a disease? Okay, if I see one variable, what if I find a customer that brought a toothpaste? How likely he is to buy a tooth cleaner, okay? A stimulant, okay? Okay. Inferring one observation from another observation. We're all familiar with that because this is the state of the art of most machine learning. Fitting the function to observation and according to the shape of the function, infer other variables that haven't been seen before. Intervention calls for some manipulation of the graph. What if I do things, okay? If I take aspirin, will my headache be cured, okay? What if we ban cigarettes, okay? See, our society has never been successful in banning cigarettes for obvious reasons. Some of them are legal, some of them are practical, but we can imagine and we can discuss what will be the case if we ban cigarettes, how much smuggling there would be from Canada and things like that. Okay. So intervention is the second level, and counterfactual, which I also label imagining, retrospection, understanding, is the top level. What distinguishes level 2 from level 3 is that this level can be inferred from classical randomized control trials, and this level cannot. Okay? And you can prove it, which means every question asked at this level, given data from randomized controlled experiments, you have two different models that gives you different answer for the same query, both compatible with the experimental data. And that's a proof that you cannot answer it uniquely. So there are distinct hierarchy. I'm telling you that you cannot answer a question at level I unless you have experiments at that level or assumption at that level or higher. The most familiar barrier is a statement correlation doesn't imply causation. Okay? You look at correlation and you cannot imply the causation in the sense of the results of my intervention. Okay? But the same barrier holds between level 2 and level 3. Okay? Here on the left, I just put provocative images. These are the degree of intelligence we have, owls and machine learning today, robots today, okay? And this is the level of sophistication we had in about most of human development, and what the child has in the crib, but still the child continues to climb up because the child wants to reach a sensation of being in control, and being in control means I understand why one toy makes noise and the other one does not make noise. Okay, so the child thrives to reach this level of understanding. Okay, and here we have the Einstein and the scientific revolution, which could not have happened in such a fast super evolutionary speed as we have seen today in the past. Well, some people say in the past 50,000 years, which is also just a blip on the evolutionary scale. In the book of Why, we attribute that to discovery of that took place about 50,000 years ago. It was the first figurine artwork which describe a object that doesn't exist in the real world. It was a lion head with human body. Such elements do not exist, but the artist could imagine the combination of a lion head and human body and try to express with that combination some ideas that I wish as a human I would like to be as brave as a lion, perhaps. But that ability to put things together that do not exist in the experiential world was the trigger that, according to Harari, okay, enabled Homo sapiens to dominate the planet, despite the fact that the Neanderthal and the Homo erectus were more developed in terms of bodily ability and even brain size. Okay, I'll go from philosophy now to more tools, practical tools. The second law that I talked about was reading in dependencies from the graph. Okay, I know many of you are teaching a graphical model, so I wouldn't need to elaborate except to summarize things quickly of this wonderful, which for me is a miracle, that you are able to look at the graph and tell something about what you expect to find in the data. Okay? So the idea is that every time, here by the way, is a society of listening agents. You see, these are just functions. The rain is listening to the climate, the wetness of the ground is listening to the sprinkler and to the rain, and maybe some other variables, maybe the neighbor's dog, okay, which are exogenous, so I don't put them here. And this is an abstraction of that. We don't have, and we're never going to have those functions. But look how much power we obtain just from imagining that they exist. So first is the ability to tell what to expect in the data. Every time you see a missing link, here missing link, here missing link, you should expect some conditional independence in the data. Do I show it here? Yes. Here. A missing link with C and W. I can tell you that if you believe if the model is correct, then you should expect to see C independent on W, giving the separators S and R. Same thing about that, with a little glitch. Here I'm not putting the collider, I'm skipping it. I'm just saying C is independent of W. Up, I missed that. I should have another one saying it S is independent on R, given C. Okay. What can I do with that ability? Marvelous things. Number one, I can do model testing. Every time I see violation of this model prediction, I declare the model to be incompatible. Additionally, I can talk about structural learning. I can look at the set of models which are compatible with data and try to do something with the set. Perhaps they all give me the same answer on my research query, in which case I like to have a set. And perhaps I can condense the set into also a parsimonious representation. That has to do with structural learning. And what I'm going to get into, you reduce interventional question to adjustment and to a calculus, to symbolic calculus. And this is what I'm going to show you right now. Okay. So here's an operator, do X. I can emulate, I can interpret it first in terms of chopping off the incoming error. What I mean by forcing X to obtain the value small x is I have to force it, right? I have to chop off all previous influences on X and subject X. Let's say I turn the sprinkler on. Sprinkler was connected to automatic controller. If I want to turn the sprinkler on, I'm going to dislodge all previous influences on my sprinkler and subject the sprinkler to enslave the sprinkler to my muscle. And that's what I mean by chopping off those entering influences and fixing the value of X to on or off, and then see what happens in the universe. But I can emulate it also on the original graph by chopping off all ongoing influence correlations between X in the backdoor to Y. So I do that. If I can observe Z1 and Z4, I accomplish the same thing as cutting off those errors. Why? Because all the spurious correlation between X and Y, which go through some confounders, common causes between X and Y, will not be able to transmit information. And that will give me the ability to compute the expected value of Y given that I do X. This is called the backdoor criterion and allows me to do many things like say, do I need really to control Z1 and Z4? It's quite costly. Perhaps I can manage just measuring. Here I'm not doing anything. I just measure the value of Z4 and Z and do as well. And you have a trade-off because buying this information may be less costly, or perhaps the number of values for each of these variables is much lower. The cardinality is lower than Z1, okay? So I have a choice here of how to control for my, confounder so that still guaranteeing that the results will be valid. And that's called identification. Identify this causal question by reducing it to a statistical question. Here, it's now reduced. It says that the answer to my query, research query, what the probability of Y if I do X, is reduced now to a statistical expression. Find the sum of, here's the conditional probability statement. I can estimate it by regression. Multiply by another probabilistic stem and sum over Z. That's called adjustment. And this reduction is essentially going from level 2 intervention to level 1 association. And what gave me the power to compute, to be able to cross the line, to cross the barrier between level 1 and level 2, answering question at level 2 on the with the expression of level 1. What gave me that power? My causal assumptions. Those are the errors, essentially lack of errors in the graph. Those carry the causal assumption. The lack of error here, the lack of error between Z2 and X, and so forth. So here's an example of her assumption in level 2 give you the power to obtain data at level 1 and get an answer to level 2. Application, here the typical application that Schreier and Platt gave in sports medicine. I want to find out if warm-up exercise increases or decreases injury. And the well, Schreier is a sports physician. He knows everything about it. And they put down the kind of factors that could play a role in that decision. Okay? And data may or may not available on these factors. Some of them are very hard to get, and some of them are easy to get. So here you have a conception based on simple question: who listens to whom? Put it down enough. Once you put that model down, your answers can be obtained by algorithmic wisdom. Here's the wisdom. If you have access to Z1 and Z2, you are done. If you have access to Z1 and this one, you are done. Don't bother look at previous injuries. They are collider and they give you trouble and so forth. Okay, I just want to give you a flavor of how things go from philosophical and logical viewpoint. So I wouldn't ask you to follow the equations, but just to smell the flavor of the reasoning here. Here's another thing. I have it going beyond adjustment. First, let me go back. What do you have in adjustment? Every time you can put down a graph like that, you have a query about intervention, I can tell you whether or not you can reduce it by adjustment. Namely, whether there is a set of variables that if you measure them, your question is answered. This is called by adjustment. But going beyond adjustment, here's an example. I want to find the effect of smoking on cancer. When I am not able to find and adjusting variables. I have here a genotype which is unobserved, which causes some people to smoke, to crave for nicotine, at the same time put them in cancer risk. But I have an observation here about the tar accumulating in their lungs, and I can ask, if I do have data on smoking, tar, and cancer, and I don't have data on the genotype, can I still find an answer to my query? The goal is find this one, probability of the cancer, given that I do smoke or I do no smoke, okay? Here is the flow of the reasoning. This is what I want, my query. This is what the data I have. Probability, joint probability distribution on S, T, and C. That's all I have. Can I get that from that? And the answer is sure. How? How do I know? I submitted it to my faithful do calculus. Of course, I don't ask you to follow the steps, but believe me, the steps are all legitimized by graphical condition that allow me to go step by step. Each step is authorized by a certain graphical condition, allow me to get from a situation here where my query involves a do to my desired query, estimand, where it's full of probabilistic expression, no do appearing here. That tells me, yes, you can do it. That's the flavor of the reasoning. And these are the rules of the do calculus, which allows you. Here are the license giver. If certain condition holds in the graph, you are allowed to replace, to ignore certain observation. Other condition give you a license to replace a do term with observation, which means action with observation, and or to ignore action altogether. Okay, that's the flavor. Now it's reduced to an algorithm which turned out to be complete. Complete is a beautiful thing. Why? Because complete tells you that you don't have more, you don't need more rules. It tells you that if your algorithm failed to reduce the query to a do-free expression, no one can do better. Which means no smart machine learning or smart mathematician could find a way to answer the query. The query is simply unanswerable with the given assumption. You need to either make more assumptions or take more data from different set of variables and so on. Good. And that's a very comforting property, having completeness. Okay. Good. Now I'm going to what the science add to machine learning, and I would like to get into some application. So let's first talk about combining data with prior causal knowledge. No, the data fusion problem, because data fusion problem appear in various disguise in machine learning. They sometimes call it transfer learning. Sometimes they call it out of distribution, all kind of name for a problem that remains an obstacle in machine learning. And according to Shulkov, it never took off because it requires a solution in terms of causal modeling. So imagine that you want to combine the results from several experimental and observation studies, each conducted on a different population under different conditions, and you want to come out with an answer to yet a different, you want to find an estimate of effect size in a new population, unmatched by any of those studies. This is the most general setup. Okay. In most cases, you want to find a population change, and you want to transfer what you've learned on the existing population about another population which has changed in its character. Maybe they all got a good word about the drug and everybody become eligible to get the drug, okay? So you have a different population and you want to generalize from one to another. Just an example, but it happens across the board, okay? So what can we say about 5 minutes? Well, I have to hurry up. Okay, give you an example of how this can happen, collecting data from various hospitals. Each one has different population, different conditions. what can you say about Arkansas? Okay. It cannot be done in verbal world, but it can be done with the mathematics of transportability. If you have a model of commonalities and disparities between the different environments, and this is the kind of models, then you can do it. So what can we say? We can have a complete algorithm for the questions of that nature, and it's called transportability, it's called fusion, and so on. The algorithm is complete. Beauty. No one can do better. Another question is selection bias. You select people to randomized experiments, and you find that most of them are unemployed, homeless, okay? And they are different kind of people that volunteer for the different, they're not representative of the population, which is going to use your results. There is a way of recovering from it. If you have a structure, you can recover sometimes from selection bias by a different set of rules, also relying on the do calculus. And here I'm applying a do calculus, and I get recovery from selection bias. Okay, I want to go to personal medicine because this is something which is currently bugging me, because I believe that the future of personalized medicine lies in this ability. Okay, what can I say about it? I say the difference between population-based decision-making and personalized decision-making is the fact that we want to improve the probability that an individual, you, will attain a state of an outcome which is higher than the state of outcome if not treated. Okay, I have to, because I'm in a hurry now, maybe talking, okay, anyhow, we want to focus on individual and say we want to quantify the probability that this individual will improve, namely will be healthier than he or she would be if not treated. Okay. Focusing on the individual. And today we can do it by relying on two tools. One of them is the calculus of counterfactuals. It allows us to relate individual in one environment to another. And the second is the ability to combine data from randomized experiments and observational studies. Okay. These two gives you information about the behavior of each individual. So I cannot show you any success stories here. I just want to tell you the application. For instance, in a question of attribution or blame assignment or legal setting, you want to know whether it was the drug manufacturer responsible for the death of my client, Mr. A, who would be alive today had he not taken your drug. And according to the court, according to the criterion published in a law manual, the court must decide whether it's more probable than not that Mr. A would be alive but for the drug. This is a criterion. And you can see but for is a counterfactual entity. Had he not taken this drug, he would be alive today. We have a statement today. We have a formula for that criterion. Once you have a formula, you are done. You submit it to an algorithm. An algorithm grinds, find the bounds on this entity, find whether it is greater or smaller than 50%, because the court says more probable than not. You find out, wow, the guy is guilty 100% with 100% certainty because the bound happens to be between 1 and 1. I made them turn to be 1 and 1 just to demonstrate that a certain combination of observational and experimental studies enables you to identify this entity, probability of necessity, and sometimes it happened to be near 1, which means the guilty verdict is justified. I think, oh, I'm 3 minutes over my time, so I wouldn't get to talk about social intelligence, but this is a blue sky dream. Why blue sky? It's blue sky which is founded on some, have some basis. We are able today, we are sitting on a gold mine because we are able now to have a computational model for a state of understanding. If you can understand environment, why shouldn't you be able to understand another agent? Okay? And that is the basis for social understanding. Ability to perceive and to infer whether the agent is trustable, whether he is empathetic, whether he is aware of what you want him to be aware of, and so on. All these are relationship which makes sense only if you have a model of the agents. So I envision here development of something which I call social intelligence, the result of which would be robots that communicate with each other the way you and I communicate. Again, in terms of empathy, being aware of, and so on, and trust. Well, trust. I reached the limit of time. I'll be happy to answer any questions. And thank you for being so attentive. Thank you for not interrupting me. Usually I have some students raising their hands and say, and what about if I don't have a model or something like that? So ask me.
Thank you very much, Yuda. And I would like to open the floor for some questions. Eric.
Here's my answer.
Eric Miolik.
No, I didn't have that.
You didn't? So there was another Eric, maybe this is Tala Parasha. Okay,
yeah.
Go ahead.
I can ask a question. Thanks for a very talk. I'm a PhD student from Northeastern in Boston. So my question is that I'm very curious that why does modern medicine work so well? Because I'm more convinced by your talk that just using randomized controlled trials don't really reveal a causal relationship. But I would expect then those randomized controlled trials to not work very well for modern medicine. And like how, if we use these kind of analysis that you're presenting, how much benefit would we have in terms of medicine, for example?
You are surprised, you said, that the randomized controlled trial works so well. And
not work so well. That works.
I do not?
I don't know. Where?
Yeah, I'm surprised that they work so well because based on your talk, I'm more convinced that they don't actually reveal a causal relationship as I used to think.
Okay.
So the question is, what would the study of, what would level 3 counterfactual add to the, what you call is evidence-based medicine, right? Which evidence-based, for those who do not know, is a group of researchers who decided that nothing should be relied on except if it's based on a randomized controlled trial. So definitely everything the evolution of mankind wouldn't be justified because it is based on counterfactuals, okay? At least according to my theory. Okay, okay, here let me give you one example of what it cannot answer. It cannot combine results of two randomized controlled trials. I know that you do it. I know that physicians and researchers, statisticians, are looking to two different results of two randomized controlled trials coming from two different hospitals, right? And they are able to conclude, to put them together in their mind, okay, properly, sometimes wrongly, but most of the time correctly. Why? Because in their mind, they know the commonalities and diversities between these two environments. They generalize from a laboratory to the field. They generalize from mice to men because they know that mice have the same digestive system as the monkey and men have the same digestive system. So at least everything which is connected to digestive is generalizable. But when you talk about cognitive ability, mice and men differ, right? So they wouldn't, and they do it in their mind. Okay? Now we do it algorithmically. Why? Because we have a calculus for commonalities and diversities. And because everything you can do algorithmically, you can do better. So that's one answer. One aspect where this algorithm can do that currently is not being done in the field. The other is personalized medicine. Have you ever seen anybody define personalized medicine? Look in the Wikipedia and see how they define it. Look in the encyclopedia and Wikipedia and see how they define time to, number needed to treat. Okay, this is their conception of the number of patients you have to vaccinate before you get one improvement, one person who really benefits from the vaccination. Okay. Okay. Look at how it is defined wrongly in the Wikipedia, which we just discovered yesterday. That's why I'm so excited. We find a mistake in a 3-decade-long literature. Okay? They do things wrongly. It's time to repair.
Is there any other question? There is one question in the chat, but okay. So let me read this one. I have, and this be maybe the last one. I have a question. What if an intervention would disrupt the system, put it into a probability 0 state? To continue to, so in the sprinkler analogy, if putting the sprinkler in a specific position that we are trying to investigate would actually break the mechanism, does that theory account for such situations?
No, the theory only accounts for possibilities that are within the theory. If you want to contemplate what happens if I turn the sprinkler on and a nuclear disaster turns, you have to put it in the model as possibility. Put down a link between nuclear disaster, okay, and the world, put a link between them, quantify it with some probability 10 to the minus 18, okay, but have it in the model. If it's not in the model, I cannot answer any question about it.
And do you want to address the question maybe of where do you get the model from?
Yes, because I know it's in the mind of every data scientist. Okay, why? Because today data scientists are handcuffed with two constraints. One is they want to work without a model, data only, because eventually, Einstein too developed from amoeba, right? So if Einstein developed from amoeba, why shouldn't we do it from a neural net? We start with a neural net, have it mutilate itself and simulate evolution, and zoop comes an intelligent being. It's a good, we have existence proof that it can be done, right? So that's one constraint. The other constraint, they like to do things in terms of neural circuitry, because they feel they are close to the way really the brain works. Okay? So these are two reasons why they shun emotionally the idea of starting with a combination of a model and data. Now, if you don't have a model, you can wait for evolution, but we don't have, in many cases, we can't wait. And there is a precious wisdom in the minds of biostatisticians, epidemiologists, about how disease spreads from one country to another. We have to tap this knowledge and give an answer to society within weeks, or maybe days. We can't wait until evolution gives us that answer. So number one, expediency. Study SMC because we cannot wait. Number two, if you know SMC, you know what to look for. So if you're looking for it, if you want to search for it in the data, okay, it's very hard to find a needle in a haystack, but it's almost impossible if you haven't seen a needle before. And here I'm giving you the needle. This is what you're looking for. SMCs, this representation of understanding. Okay? That is the oracle. So you know what to look for. Third, study SMC because it helps you suppose you find it. You don't know how to use it unless you study SMC. And you have to study this separation, and you have to study adjustment set, and you have to study do calculus. This gives you the results once you have it. Otherwise, you find it and you wouldn't know how to use it. And there is a fourth one, the answer to which is also study SMC. Eventually, you have a human user to convince that he or she should follow your recommendation. And he or she is bound by explanation, needs to find explanation. And the explanation that the user accepts is causal explanation. So eventually you have to know how to generate explanation to the user to make yourself trustable, to make sure that the user keeps on trusting your recommendation. So you have to be able to generate explanation, and SMC gives you that ability. So here are three reasons why every student in data science should learn SMC. Okay. Today, only one of every, I made a quick calculation, one of every 1,000 deep learning students knows SMC, okay, which also correlate with the fact that the disproportional investment of society in deep learning and in machine learning is so tailored or so skewed toward model-free studies that both all the resources, all the focus on education goes into this machine learning, rather than a combination of model and machine learning, which I'm proposing here. Okay, so here you have a 4 reasons to study SMC, and I hope I answer your question.
Yeah, Thank you very much, Yuda, for fascinating talk.
Thank you.